Good morning students. Chapter 7 System of Particles and Rotational Motion. Yes, we have discussed about what is angular position, then angular speed, angular velocity, angular acceleration, and then we have obtained two relations. Relation between linear speed, angular speed. Relation between linear acceleration, angular acceleration. Yes, we have discussed. Also, equations for rotational motion. Okay, but see, this all part is included in kinematics of rotational motion. Now we will discuss dynamics of rotational motion. Dynamics means not study of only motion but of its cause also. So now why or how object performs rotational motion? What is reason? We know in linear motion, in translational motion, due to some external force, object is performing linear motion. Due to some external resultant force, object is performing linear motion, translational motion. So what is reason behind rotational motion? What is reason behind rotational motion? Okay, if you want to rotate any object, how will you rotate it, or how object is rotating? Okay, is only force responsible for rotational motion? Yes or no? We will see some examples. See, here it is. See, now this door about this hinge, it performs rotational motion, that we know. If I want to open or close this door, then yes, if I apply a large force at this point, will it rotate? Will it perform rotational motion? No. Why handle is placed at this end? Why handle is placed at this end? What is reason the handle is placed at this end? Can we put this handle at this end? No. Why no? Because if you put handle at this point, with the help of larger force, we can close or open this door. But if you put this handle away from these things, away from this support, then with the help of very small force, you can open or close door. So yes, for rotational motion, not only force, if I am applying a large force at this point, this door will not open. Or close. Okay, but if I am applying force at this end, see, it will easily rotate. Clear about this? So yes, in rotational motion, not only force plays the role for rotational motion, it also requires some distance, some perpendicular distance. It is hinge. Okay, so from this support, the force requires some perpendicular distance. If this perpendicular distance is more, then force applied is less for rotational motion. Clear about this? Okay. For example, see, it is pen. Okay, I am holding this pen from this end, means it is fixed end. Now if I apply force in this direction, will it perform any rotational motion? No. But now if I apply force normal to it like this, yes, like this, so see, it will perform rotational motion. If you apply force normal to it, it will perform rotational motion. Yes or no? So see, every force, if I am applying force in this direction or large force, okay, it will not produce any rotational motion. So for rotational motion, only force is not enough. It also requires some perpendicular distance. Clear about this? So yes, these points for rotational motion you have to remember. Yes, there are numbers of example. If in fan, yes, you have 3 fans. Okay, try to rotate fan from its center. It will be difficult. But now try to rotate fan from end. It will be easy. It will be easy. Why? Because rotational motion, how to produce rotational motion, it depends on force and also distance. Clear? So yes, there are numbers of examples. If you are moving on bicycle or Activa, okay, the handles, okay, they are given like this at some distance, so we can easily turn your vehicle. Yes or no? Can you turn your vehicle if that steering is only at its center? Okay, it's difficult to rotate. It is difficult to rotate. Clear? So yes, for rotational motion, only force is not responsible. Some perpendicular distance is also required. There are numbers of examples. Okay, yes, you can easily observe this. Okay, so now we will see its theory. First theory of about this is torque. What is torque? Yes, for linear motion, force is required. For rotational motion, torque is required. Okay, you see, yes, due to force object performs linear translational motion. Okay, rotational analog of force is torque. Okay, now torque. What is torque? Torque is also called moment of force. Torque is also called moment of force. Okay, it is denoted by tau. It is denoted by tau. Okay, tau. Yes. Now, a torque acting on particle. So yes, we will assume some data and we will find what is torque acting on particle. See, for example, x-axis, y-axis, origin. Yes, torque acting on particle. So just I am taking, okay, here it is one particle. Okay, let its position vector from this is r. Its position vector is r. Okay. Now let force acting on this particle. Force acting on this particle is F. Force acting on this particle is F, like this. Okay. Now see, force is acting in this direction. Position vector, its actual direction is in this direction. I am assuming angle between force and position vector, that is theta. I am assuming angle between position vector and force, that is theta. So as shown in figure, position vector of a particle, is r. Force acting on it is F. Angle between F and R, that is force and position vector, is theta. So torque acting on this particle with respect to O. Torque acting on this particle with respect to O. Torque acting on particle with respect to O is defined as tau is equal to R cross F. Tau is equal to r cross f, where what is r? R is position vector with respect to O. R is position vector with respect to O. F is force. So tau is equal to r cross f. Tau is equal to r cross f. That you have to remember. Okay. Its magnitude. Therefore, its magnitude. How to write its magnitude? Tau is equal to, yes, you know, A cross B is equal to AB sine theta. So r cross f is equal to, it is rf sine theta. Where r, f, and here it is sine theta. I can also write this equation as, see, tau is equal to, it is f r sine theta. Tau is equal to, it is f r sine theta. Now what about r sine theta? See here. Hello, here. If I draw line of action of this force, okay, now draw perpendicular distance. Now draw perpendicular distance from origin on this force. Okay, it makes angle 90. It makes angle 90. So this ON is perpendicular distance. This ON is perpendicular distance. What you have to do? Okay, draw perpendicular from O on line of action of force. On line of action of force. It is called line of action of force. Okay. You have to draw perpendicular. Next, it makes angle 90. It makes angle 90. Clear about this? Okay. Now see in this figure. If this angle is theta, obviously this angle is also theta. This angle is also theta. Clear? Any doubt? So see, this ON is opposite side of angle theta. It is right angle. It is right angle, so this R is hypotenuse. Okay, it is angle theta. So this ON is its opposite side. Yes or no? And this is hypotenuse. So yes, opposite side and hypotenuse. So obviously, which trigonometric function you have to use? Yes, you have to use sine theta. You have to use sine theta. Okay, sine theta is equal to, it is ON upon R. See again, sine theta is equal to ON upon R. So ON is equal to, it is R sine theta. ON is equal to, it is R sine theta. So now in this equation, I will replace R sine theta by ON. So therefore, tau is equal to F. And here it is ON. And here it is ON. Clear? Any doubt? Okay. So tau is equal to, it is F into ON. Tau is equal to, it is F into ON. Now what is F and what is ON? See, what is tau and what is ON? Here it is. Here it is. See, torque is equal to F means force into, what is this ON? ON is called, see, draw perpendicular from O on line of action of force. Means this ON is called perpendicular distance of line of action of force from O, that is center. Okay, perpendicular distance of line of action of force from O. Clear? This torque is with respect to point O. This torque is with respect to point O. So it is definition of torque. Okay, what is torque? Torque is equal to force into perpendicular distance from point. Torque is equal to force into perpendicular distance from point. This definition you have to remember. Torque is equal to force into perpendicular distance from line of action of force. So see, this torque now depends on force as well as perpendicular distance. So if distance is more, then obviously torque is also more. Yes or no? If distance is more, torque is also more. If distance is 0, perpendicular distance 0, then obviously torque will be 0. Obviously torque will be 0. Yes, remember again that example of pen. So suppose it is pen and I am applying force in this direction. So see, this line of action of force, it is passing from this point. See, I will draw here this. Okay, suppose it is pen. It is fixed from this point O. Okay, now I am applying two forces. First force F1 like this. Second force F2 like this. Okay, so see, as this F1, its line of action is passing from F1, it will not produce torque. It will not produce torque. But see, this F2, it is its line of action and it has some distance. For example, it is R. So this F2, it will produce torque. It will produce torque. Simple? Yes or no? Yes, it will produce torque. Clear about this? So yes, and what is torque due to this? So torque T is equal to it is force is F2 and perpendicular distance is so yes, it is one example. Due to which forces torque is produced and it will perform rotational motion. Yes, if this force is F2 is applied in this direction, it will perform rotational motion in this direction. Clear about this? Okay, so yes, it is definition of torque acting on particle. It is also definition of torque. Okay, you have to remember this equation. It is most important thing of this chapter. Okay, now what is unit of torque? What is unit of torque? Unit of torque, see, it is force into distance, so it is obviously Newton meter. It is Newton meter. Now see, torque is equal to R cross F. R cross F means torque is vector quantity. Torque is vector quantity. Torque is vector quantity. And its direction according to right hand screw rule, is perpendicular to plane of R and F. R and F means it is perpendicular to both R and F. So yes, this point you have to clear about this. Okay, so yes, its unit, its direction. Now, whenever you have to find torque, you have to mention that reference point. That here, torque with respect to point O. Perpendicular distance of line of action of force from O. So yes, you have to mention reference point. Okay, to find torque, mention reference point. Clear about this? So yes, in each and every case you have to mention reference point. Reference point means what? From which point it is rotating. From which point it is rotating. It is called reference point. Clear about this? So it is all about torque. Okay, what is torque? For rotational motion, is only force responsible? No, force only is not responsible. Okay. One quantity which is responsible for rotational motion is torque. And for a particle, what is equation of torque? Torque is equal to it is force into perpendicular distance. Its unit is Newton meter. How to find its direction? See, tau is equal to it is according to R cross F. Means torque is acting perpendicular to both of these. Clear about this? Okay, see again, it is one important topic. What is torque? Okay, you have to observe objects which are performing rotational motion and how they are performing rotational motion. Try to rotate some objects. You are applying force in which direction, so they are performing rotational motion. And understand. Okay, you will get an idea. And if you do not get idea, yes, I am always there. So yes, it is all about torque acting on particle. You have to write this. Okay. One extra case, see, okay, if you are given one body like this, from this point O it is fixed, and force is applied in this direction, then yes, is this force responsible for rotational motion? No. This force totally is not responsible for rotational motion. We have to resolve this force in two components. It is F parallel and it is F perpendicular. So again, see, if you know this, you can easily say, sir, this F parallel, it will not produce any torque. This F perpendicular will produce torque. So yes, whenever you are given forces like this, you have to understand, okay, you have to think, yes, due to which component it will perform rotational motion. Again, see, due to this torque is fixed from this point. If I am applying force in this direction, will it perform any rotational motion? No, simple. But if I am applying force perpendicular to it like this, so obviously it will perform rotational motion. Simple. Clear about this? So, for torque, force as well as perpendicular distance is required. Perpendicular distance is required. Then and then it will perform rotational motion. If I am applying force at this point, at fixed point, suppose F, okay, suppose F, I am applying force at this point, it will not perform any rotational motion. It will not produce torque. Okay, similar example in door, in case of door, okay, if you apply force from that hinge, okay, it will not perform rotational motion. Simple, clear? So yes, it is one most important concept of this chapter, that is rotational motion, and it's all about torque. And yes, this is it for today.